This is 2.4. We're using rates of change to create a graphical model. This section stands out like a fish out of water. It represents a verbal description of rates of change using graphs. Jesse, can you read?
Today, Steve walked to his part-time job. As he started walking, he sped up for 3 minutes. Then he walked at a constant pace for another 2 minutes. When he realized that he would be early for work, he slowed down. His walk ended, and he came to a complete stop when he reached his destination 10 minutes after he started.
Okay, good. When did you guys first see this? Was it grade 9 or grade 10? You started using those motion sensors. No, in math though, we did these drawings, right? In grade...
Oh, in grade 9.
I think it's grade 9, right? Yeah.
I had Marinelli. Shabab did it.
And you had to try and replicate graphs. This is the exact same idea, guys, with this section. Gianluca? Gianluca? It's the same idea. The only difference is that you're using exponential curves, or we don't necessarily always have constant rates. Okay, so this would be typical of a grade 9 question. You see everything's constant, and then this is a typical grade 12 question where we start to see curves in the graph, okay, which represents speeding up and slowing down. Okay, that's the only difference, but the idea is the same. It's going to be hopefully pretty straightforward. So it says, what would the speed versus time graph look of Steve's walk to work? So create a speed versus time graph for Steve's walk to work. So first of all, it tells us he's walking to his job. He started walking, he sped up for 3 minutes. As he started working, he sped up for 3 minutes. So from 0 to 3, okay? Be careful now. This is speed versus time, not distance versus time. There's a difference. When we did those graphing calculators and those motion sensors in grade 9, we were always doing distance, I believe. So it was like distance from the sensor, right? So this is speed. So it says he sped up for 3 minutes. So for 3 minutes, he's speeding up. His speed is going up. Then he walked at a constant pace for another 2 minutes. So like on our distance time graph, when did we get horizontal lines? When what was happening? Yeah, when he wasn't moving, when he was standing still. In this case, be careful, he's actually still moving here. Okay? He's just moving at a constant rate. Okay, Alan? So can you explain this next part here? Alan, from 5 to 10, what's happening?
So he's slowing down for the last 5 minutes?
Right, so exactly. So he's slowing down from this minute to the 10th minute. So that's why the graph goes down. So the whole time, though, in this graph, he's moving. Okay? Whereas you might kind of get the opinion that he might be stopped here. He's not. He's moving. He's just going constant, and now he's slowing down. Okay? He realized that he would be early for work, so he slowed down. His walk ended, and he came to a complete stop once he reached his destination 10 minutes after he started. So only when speed is 0 is he stopped. So he stopped here, and he stopped here. Those are the only 2 times. Okay, any questions there? All right. So this first one, I missed that part, the solution A, it says, assuming that he changed speed at a constant rate. So this means that his speed was changing or increasing at a constant rate. Okay, so it was a straight line. This means that it took him a while. He like picked up a quick walk, then he started jogging, and now he's like running. And then he runs at a constant speed. And now he starts slowing down. So this is a more like natural, realistic representation of a run. Okay? We're not robots. We can't just go from one speed to another. It does take us a little bit of time to transition to a higher speed. Right? So this graph is actually pretty inaccurate, right? We can't really just do this. We can't go constant, and then slow down all at a constant rate. No, this is much more realistic. Okay? So let's read what it says. Because Steve was speeding up, his speed increased as time increased. His speed increased at a variable rate. So you might draw an increasing curve that starts at 0, 0 and ends at x equals 3. So again, slowly speeding up quick, speeding up really quick, running at that same speed, which is up here. Let's say he's running at 1, 2, 3, 4, 5. Let's say, I don't know, 15 kilometers per hour is a reasonable run speed.
Didn't start at 0.
No, you're right. He didn't start at 0 either. It looks like in this graph he was walking originally.
It says though that they're supposed to start at 0. 0.
Where?
At the top.
So you might draw an increasing curve that starts at 0, 0 and ends at x equals 3. Yeah, I'm not sure why. Do they mention that? No. Between 3 and 5, Steve walked at the same rate. All right, so I don't know if he was crawling. If he's walking here at the fastest rate, maybe he was crawling over here. Because they're saying that they're saying he's still walking here.
Maybe he's just speed walking.
Who knows what these units are, right? They don't give us these units, so this could be like 5 and this could be like 5.02 or something. It could be very minimal change, right? We don't know. We don't know. All right. Whatever.
So the straight line he's walking?
Yeah, he's not changing speed. So it's the same speed. He's still moving, but it's at the same speed. Okay? Yes. No, he is running. He's running or whatever he was doing at the fastest speed. Constant, yeah. Okay, which details in the given description were most important for determining the shape of the graph? I don't know, I would say like all of these points, right? These were the most important. When did he start? When did he stop? And then when was he running constant? Okay? Are these the only two graphs that could represent Steve's walk to work? Explain. No, there's a whole host of different ways he could have sped up, right? Okay, any questions about that one? Example 2 now. A flask, a beaker, a graduated cylinder being filled with water. So there's water going into all of these. The rate at which the water flows from the tap is the same when filling all 3 containers. Draw possible water level versus time graphs for these containers. So graduated cylinder, which is this one, because it has a constant diameter, the rate at which it fills up from the bottom to the top is going to be what? Yeah, it's going to be the same, right? So the height is definitely continuing to increase, but the rate at which that height increases over time is the same. That's why we get a straight line. Any questions with that one? You'll notice with the beaker, it's the same thing. We have a constant radius or constant diameter, so it also has a straight line. It has less of a slope because it's wider, and so more water has to enter before it can raise its height. That's why the height takes longer to get to the same level as the graduated cylinder. Does that make sense? And finally, the flask, because at the beginning it's really wide, the height is going to increase slowly. Okay? But then as it gets to the top, like you all know when you fill up, yeah, a water bottle gets fast at the end because it's narrow. Okay, so that's why it speeds up. Okay? Any questions? All right. Example 3. My voice is getting raw here. Who'd like to read example 3? Luigi, thanks.
A cyclist is observed moving at a speed of 10 meters per second. She begins to slow down at a constant rate, and 4 seconds later is at a speed of 5 meters per second. She continues to slow down at a different constant rate and finally comes to a stop 6 seconds later. A. Sketch a graph of speed versus time. B. What is the average rate of change of the cyclist's speed in the first 4 seconds? C. Estimate the instantaneous rate of change in the speed at 3 seconds.
Okay, good. So I think this is, again, relatively easy. Pretty simple graph to draw. It tells us that she's moving at a speed of 10. She begins to slow down. So speed versus time, speed at 10 at the beginning. Okay, so we start observing her at 0. Obviously, you know, she had to do something to get to that speed initially, but our observations start at time 0, and she's already moving at a speed of 10. Okay, she begins to slow down at a constant rate. Constant means straight line. Okay, so she's slowing down, her speed is going down, and 4 seconds later is at 5. So she goes to 5 4 seconds later. She continues to slow down at a different constant rate and finally comes to a stop 6 seconds later. So we know that this slope, we actually know that this is the line. It doesn't tell us the rate at which she slows down, but we know she's coming to a stop at 10, and we know that it's constant. So we know we have to connect these two dots. So we actually know this line. All right? Sketch a graph of speed versus time. So there it is. What is the average rate of change of the cyclist speed in the first 4 seconds? So how am I going to figure that out? Lyndon.
So what's the average speed first? So you take 2 points off of the line.
Which points?
You can take the, I don't think any points really matter, but you take the first point and after
This point, yeah.
between 1 and 4.
Right. Yeah, that's important. Okay, so you're right. It doesn't matter if I take this point and this point and this point and this point because it's a straight line. But you know, the easiest points are going to be these two because we have units for them, right? So we're going to take 0 and 10 and 4 and 5. And then what do I do?
And after you're going to go y2 minus y.
Right.
Over x2 minus x1.
And that's right here. Yep. Okay, so it's negative. Why? Because it's negative. It's going down. We're slowing down, so our speed would be negative. Okay, and average rate of change is just a really fancy word of saying the slope. Slope of secant. No, instantaneous rate of change. Or in calculus, or derivative. Is the slope of tangent. That's it. Yeah, so now you can tell somebody you know what a derivative is. And you can explain it to them. More importantly. You don't just regurgitate, oh, it's the instantaneous rate of change. That's a derivative. No, you say, well, actually, if the graph looked like this, it's this line, and it's the slope of that line at the point you're looking for the derivative. Okay? All right, number C. Estimate the instantaneous rate of change in speed at 3 seconds. So here, this is where we use that process now. So 3 seconds is our point of interest, so that's right here. Here's our point of interest. And it says instantaneous rate of change. What's it going to be right here? If we draw a secant line on any other point, what's it going to be? Do we already know what it is? Nicholas, what do you think? Instantaneous rate of change at this point. Okay, before, don't look at this. There's a line here, right? The instantaneous rate of change is what? What did I just say up here? What did I say it was? Okay, so what's the slope of the tangent of any of these points? Right, it's the same. It's the slope of the line, right? We talked about that the first day in this chapter. We said the slope of a straight line, the tangent of a straight line is the straight line, right? Like I can't draw a tangent to any of these points. I got to go right with them. So then, Nicholas, what is the instantaneous rate of change at this point? Point of interest, t equals 3. What would it be? 3? No. No, that's...
Do whatever the slope of the
Yeah, what's the slope? We just found it, right?
Oh, sorry. Yeah, sorry. There's 1.0.
Yes.
1.25.
So that's why. Yes.
So if they didn't slow down at a constant rate, it would be a curve, right?
Yes.
And we would find it the same way we found it in the previous lesson.
Yes. Any questions there? All right. Last example. Who said yeah? You can read. Thanks.
Adam and his friend are testing a motion sensor. Adam stands 0.5 meters in front of the sensor and then walks 4 meters away from it at a constant rate for 10 seconds. Next, Adam walks 1 meter toward the sensor for 5 seconds and then waits there for another 5 seconds. A. Draw a distance versus time graph for Adam's motion sensor walk.
Okay, so big difference. They've changed something. They're talking about distance now. So be careful. It's different. Now in this graph, if it's a straight horizontal line, he's not moving anymore. He's standing still because his distance is not changing. Okay? So this section here, he is stopped. Okay. Draw a distance versus time graph for Adam's motion sensor walk. So, tells us he's 0.5 meters in front of the sensor. So where do we start? 0.5 meters. He walks away from the sensor at a constant rate. So this is our distance from the sensor. So he's moving away. So he's walking away. For 10 seconds. It's constant, so we know it's a straight line. So all the way to 10, he's moved away from the sensor. And it doesn't tell us that he gets to 4.5 meters. So it looks like they've taken some creative leeway here and decided to stop him at put it at this slope. Let's see what they say. The graph begins with a straight line since it walks in constant. The graph has a positive slope since he walks away, and his distance from the center increased. Okay, that's fine. Adam starts 0.5 from the center. Yep. As the distance. Adam walks 4 meters away from the sensor.
Because it starts at 0.5.
So then he ends up at 4.5.
So it starts at 0.5. Does it say he walks? Oh, it tells you. Oh, okay, sorry. I missed that. No, I wasn't. Sorry. I missed that. So yeah, he walks 4 meters. So yeah, I thought they were just making that assumption. At a constant rate for 10 seconds. So there's there. So we know these 2 points. They're set in stone. Next, he walks 1 meter towards the sensor. So now his distance towards the center goes down because he's walking back towards it for 5 seconds. So from 10 to 15, he walks towards it. And then waits there for 5 seconds. So again, here, do they know that he walked this distance back towards it? Next Adam walks. Oh, 1 meter. Yeah, I missed it again. 1 meter. Okay. So he goes back down 1 meter from 4.5 to 3.5. And then he waits there for 5 seconds. So here he's 5 seconds. He's stopped. 5 seconds. Any questions on the graph, how it was drawn? That's arguably the hardest point. The hardest part of this question. What's the average rate of change in his distance in the first 10 seconds? So from here to here, average rate of change is our slope again, right? Okay, so we just take 4.5 minus 0.5. There's our y values. Okay, and we get 0.4. And that would be meters per second. Definitely has units. All right. What are the instantaneous rates of change at t equals 1 and t equals 7? Well, we're dealing with all straight lines here. So when we deal with instantaneous rates of change on a straight line, it's just the slope of that line. And we covered that in the last question, right? So at t equals 1 and 7. So 1 is here, and 7 is here. So they're going to be the same, right? Because they're on the same line.
Cool, I like straight lines. Easy.
Instantaneous rate of change is 0.4. Adam's distance for the sensor is increasing, moving away from the sensor at a rate of 0.4. Both of the tangent lines have the same slope as the secant line since the graph is linear on the interval. So you just calculate it for one, it's on the same line, it's the same value, which is 0.4.
So it's
Sorry. Any questions on that one? I see people are fading away here, so this is probably too easy. I'm take it. D, what is the average rate of change in the next 5 seconds? So again, we're just calculating the slope. Slope again. E, what is the instantaneous rate of change at 12 and 14? Again, we're just calculating the slope because they're all straight lines. So this is like grade 9. What is the instantaneous rate of change at t equals 18? What's the slope of a horizontal line? 0. Good. So F is 0. Okay. And finally, G, draw a speed versus time graph for Adam's motion sensor walk. So now we've changed it where this is our speed. So this one might be a little bit interesting to you guys. So because our distance time graph is a straight line from 0 to 10, remember what a constant speed was, constant increase. It's a straight line on a speed graph. So from 0 to 10, it's a straight line. And then from 10 to 15, it's also a straight line, so it's a horizontal line on the speed graph. Any questions about that, going from here to here? That might be...
So why don't you connect the two lines like for vertically?
like this?
Yeah.
This doesn't represent anything.
So you, okay.
like that line. Oh, okay.
So it doesn't represent the like him
No.
slowing down.
It's like a
No.
golden roll.
Doesn't represent anything. Okay.
So it's basically kind of like went and then stopped and then go back again or walk it again.
You want to discuss his motion again? He went at a constant speed up and then when it started to go at a constant speed down.
Okay.
Again, this is not the most realistic graph, right? Because there's no curves. So that's why you get something like this. Okay? Realistically, there would be a transition happening here, right? Okay.
But this is nothing.
In summary, somebody else read this. Joseph, he's on his phone. Go ahead, read this, Joseph. In the back.
In a problem that involves movement, a possible graph shows displacement, distance, height, or depth versus time. Distance, height, or depth is the dependent variable, and time is the independent variable. The rate of change in these relationships is speed. Speed is equal to change in displacement over change in time.
Absolute value.
Absolute value. On a displacement, distance, height, or depth versus time graph, the magnitude of the slope of a secant line represents the average speed on the corresponding interval. The magnitude of the slope of a tangent line represents the instantaneous speed at a specific point. As a result, observing how the slopes of tangent lines change at different points on the graph gives you insight into how the speed changes over time.
Excellent. Just aside, why is it absolute value for speed?
You can't have negative speed.
Right? You can't have negative speed. And also, there's another word for speed that we use in physics. Velocity, which can have negative values, right? Because it represents direction. Okay, speed, we're not concerned about direction, we're just concerned about the magnitude. All right, need to know, when the rate of change of displacement or speed is constant, we get a straight line. An increasing line indicates that displacement increases. A decreasing line indicates that displacement decreases as time increases. A horizontal line indicates that there is no change in displacement as time increases. So that's all interesting, but those are all distance graphs. We're a little bit more interested in the speed graphs, which are here, okay? When the rate of change of displacement or speed is variable, an increasing curve indicates that displacement increases as time increases. In other words, it speeds up. As the curve is this, it slows down. Okay, speed is decreasing as the time increases. Speed is increasing as time increases. A decreasing curve indicates that displacement decreases as time increases. The speed is decreasing as time increases. And finally, the speed is increasing as the time increases. So here, he's slowing down. No, sorry, he's speeding up here as time increases in a negative direction. Here he's speeding up in a positive direction as time increases. All right, that's it.